Cook, and I'm a student at Athabasca University, and I'm currently taking the course Computer Science 444, Embedded/Robotic Programming. And if you've been following the videos that I've been posting to the course forum so far, you'll know that I'm going through the SparkFun Inventor's Kit Guide, and I'm showing you how I've completed some of the projects and the associated coding challenges with those projects. So if you look on the forum, I've already got videos on there showing me completing projects 1, 2, and 3, along with the associated coding challenges, and in my latest video, I completed Circuit 4A, which is the first circuit in Project 4. And in today's video, we're going to be going through Circuit 4B of Project 4 from the Inventor's Guide. And I'm going to be working with a TMP36 temperature sensor and an LCD to display temperature readings in Celsius and Fahrenheit. I'll start by discussing how the how the TMP36 sensor connects to an analog pin, and how the Arduino, in our case the SparkFun Redboard, processes these readings. I'll introduce the Liquid Crystal library, which manages communication with the LCD, and explain how it's initialized with specific pins. In the setup function, I will emphasize setting the baud rate for serial communication and the dimensions of the LCD display for proper operation. As I dive into the loop function, I'll explain how temperature readings are calculated from the TMP36's analog voltage output and then converted into Celsius and Fahrenheit. I'll show how the LCD displays this information in real time while clearing the previous display to minimize noise. Then I'll transition into my coding challenge, where I expand the basic functionality by adding a menu system that allows toggling between displaying temperatures in Kelvin, a bar graph representation, a light sensor readings from a photoresistor, along with the default temperature display, which is just shown using Celsius and Fahrenheit temperatures, much like the original circuit. I'll also describe how button inputs facilitate seamless navigation through these modes, and how the RGB LED provides visual feedback based on temperature, changing colors from blue, cold, to red, hot. I'll discuss the challenges I face, particularly with managing button debouncing and effective mode switching while ensuring fluid data updates. As always, I encourage all Com44 students watching to experiment on your own, and if you have any questions, please post them on the forum. So if you followed the videos that I posted in the past, you'll know that at this point I would go through the SparkFun guide, particularly the section associated with the circuit I'm working on, in this case Circuit 4B, the temperature sensor, and although I wouldn't read the guide in its entirety, I would go through the highlights. In this case, I'm going to go a little out of order, and I'm going to start by doing the live demo. And the reason I'm going to do this is because of the fact that, well, I've already just setting up the video and doing things like that. My sweet and sour sauce, which is what I'm using to cool down the temperature sensor, has already started to melt. So I'm going to start with the live demo right now, and then we'll come back and do it afterwards. But right now I just want to get it started before my sweet and sour sauce melts any further. So just a quick overview of what's happening. The code that's currently set up on this is the code associated with the coding challenge, not the original circuit. So what that does is, in default mode, which is how the circuit starts when I first have it opened, it is, let me just get this up here. When the circuit first starts, it shows a menu option. I have 4 options to choose from as far as the serial monitor shows here. Options 1, 2, 3, or 4, corresponding to 0 through 3. The current mode I'm in is 0, and that just shows the default temperature values. I can toggle through the different modes as well, and I'll show that in a minute. But first, the main thing that's different at this point from the original circuit is I have an RGB LED that changes color depending on the temperature. So right now it's kind of a purpley pink hue, and that's because it's kind of in the middle of the range. So I have it changes to change color from blue to red, fully blue when it's at minimum temperature, which I have set as 18, and fully red when it's at maximum temperature, which I have set at 30. Now right now in the room it's around 24 degrees, 23 degrees. It's fairly hot in this room actually, but that's because my wife keeps the temperature pretty high during the winter months. But in order to get to those temperatures, I need to have a little help. So I'm going to use some cold sweet and sour sauce to take the temperature down to 18 degrees, and take a note of the RGB LED. It's going to change and hopefully get full blue by the time we get down. So you can see as the temperature is dropping, the LED is changing purple to blue, and it's almost full blue now. And yeah, that's pretty much full blue. So that is. So it's kind of hard to see. I notice it doesn't show very well in the video here, but that is full blue. Can't get any more blue than that. And as the temperature increases, it's going to go back from blue to purple to pink and ultimately to red. But let's speed up that process a little bit. So that was a fairly quick transition, but as you can see, the RGB LED is now fully red because we're at above 30 degrees, and as I showed you, I have it set up for the max temp is 30 degrees. So we can see that we've already started to change colors. We're now at a pink color as the temperature drops below 30. So that's the default mode where I show the temperature in Celsius and Fahrenheit. I can also show the temperature in Kelvin by pressing 1 in the serial monitor and pressing enter. So let's do that, and that'll toggle me into Kelvin mode. So I'm displaying the temperature in Kelvin, and that's, if you're not familiar with Kelvin temperature, you're just adding 273.15 to your Celsius degrees, and that gives you degrees in Kelvin. So considering this is 273 added onto this, that means our Celsius temperature is roughly, well, 273 degrees smaller than this, so about 27. Let's take a look and see if that's true. Yeah, we're about 27 degrees. How did I get back there? Well, I typed in 0 in the serial monitor again. Now I'm going to type in 2 in the serial monitor, and I'm going to jump to showing the temperature via a bar graph. So again, I have a fairly high temperature right now, closer to 30, which is why I've got full bars. But if I get out my trusty sweet and sour sauce again, you can see that the bars decrease as the temperature drops. Trying to get them all to drop. And there you go, that last one dropped. And that's because, again, the temperature had dropped significantly to 20 degrees. I want to go back and show you the bars. So you can see as the temperature increases, the bars will come back up. There's also this option. I can press 3 in the serial monitor and go to light mode. This shows the light level being read by the photoresistor. So when all the lights are on, it's like at 918. If I shut a couple lights off and cover the photoresistor with my finger, you can see I dropped the light level significantly. And let me just lower that a little bit. And yeah, so those are the different options. I don't have to use the serial monitor to toggle, by the way. Correction. I can use the serial monitor. For example, if I go back to the default value, press 0, I go back to the default. But I can also toggle via this black button. So I can press the button, and that put me to Kelvin temperature. I can press the button again. And that puts me in the bar graph temperature thing. I can press the button again and get to the light mode, and it'll take me then back to the Celsius temperature. So again, it just toggles through those options if I keep pressing the button. So I can do that, or I can press and toggle via the serial monitor. Either or. But again, as the temperature is increased here, and you'll notice that temperature was just reading 30 degrees, and it wasn't 30 degrees. This is a good kind of point to mention. These temperature sensors are very sensitive to electrical noise, the wiring being wiggled or anything like that. So because the wire had got moved when I, basically threw that bag of sealed package of sweet and sour sauce on this, I had jarred the wire a little bit and pulled it out, and then it was kind of giving erroneous readings. If I pulled it out completely, it would, like, pulled it a little more. Let's see. So now it's half out the 25. Now it's fully out, so now it's going to be some really weird reading. But see, depending on what state of the wire's in, like if it's being half pulled out or anything, it changes the temperature until the point where if you pull it out completely, you'll just get some really weird readings. It's extremely cold in here, it's extremely hot in here. It doesn't know what it is. It's hot, it's cold, it's a Katy Perry song. So, let's get that put back. And again, you really shouldn't be fiddling with a circuit when it's on, but in that particular case, there was really no risk, so I went ahead and did it. But so that's the live demo. I wanted to get to that a little early just because of the fact that, I'm dealing with temperature stuff. So now we'll actually go through the SparkFun Inventor's Kit Guide. So again, I'm not going to read this in its entirety. I'm just going to kind of cover the highlights. But if you have any questions, feel free to post them in the forum. So this circuit is about the temperature sensor, which is a small, low-cost sensor, the TMP36, and essentially tracks your temperature. We're also going to use an LCD screen to display the sensor readings, and that's a common use case for LCDs. So the common use of LCDs in electronic projects is to make them portable by, you're able to disconnect from the computer and still be able to show values to the user. So we have them hooked up so they can display sensor readings or anything like that, and they no longer need a computer and the serial monitor. So that is a very common use case for LCD screens. The new components that we're going to be using today are the TMP36 temperature sensor. It's got 3 pins. One hooks up to the 5 volts of your Arduino, the other hooks up to the ground, and the middle pin is your voltage output pin. So that's your signal pin. And basically the voltage output from the third leg varies proportionally to changes in temperature. So by doing some simple math with this voltage, we can measure temperature in degrees Celsius or Fahrenheit. Some of the new concepts we're going to talk about today are algorithms, and we're specifically going to be concerned with turning a voltage value into a temperature value. The formula that we're going to use, the first formula that we're going to use, takes the voltage read on the analog pin, A0 in this case, and multiplies it to get a value from 0 to 5 volts. So how do we do that exactly? Well, we do an analog read of pin A0, but any of the analog pins will work, and then we times by this number, and that gives us the voltage. But where do we get this number? Well, you can read the data sheet and figure it out, but it tells us right here conveniently. The number we are multiplying by, i.e. this number here, is obtained from dividing 5 volts by the number of samples the analog pin can read, namely 1024. So we take 5, divide by 1024, and we get this magical number here, which we then multiply by the analog read. So just to give a little more explanation of what's happening there, the ADC, or analog to digital converter, associated with the analog pins reads in a value. We're used to that. We've seen that with our potentiometer outputs that we've done. If you've been following the circuits so far and the videos I've been posting, all of the analog pins will always read a value from 0 to 1023. That's 1024 distinct values because the 0 counts. And that comes from the resolution of the analog digital converters associated with the pins. They have what's called 10-bit resolution. And because we're dealing in binary, the microcontrollers, they have states of either on or off, 0 or 1, true or false. So 2 states. 10-bit resolution means that we go 2 to the 10th power. And 2 to the 10th power just so happens to be 1024. So because our analog reads have that 1024 bits of resolution, so to speak, 10-bit resolution, but 1024 different steps of resolution, we don't want to read that. That's not what we need. We need to be able to read in a voltage from 0 to 5 volts. So we need to map that 0 to 1023 to 0 and 5 volts. And we do that by taking 5 volts and dividing by 1024. We're saying, hey, take 5 volts and divide it by the resolution you have, and it gives us this number. So now if I times this value by each individual step out of the 1024, I'm going to get values from 0 volts all the way up to 5 volts. So I'll kind of just show that via the calculator right quick, just to make it a little more clear. So, for example, if I read in about halfway, if I read about way on the analog read, I wouldn't get a value of 1024. I'd get a value about 512. That'd be about halfway. And if I times it by this number, .2813, I should expect, if my analog read is half, of what it could be, and I'm timesing by this number in order to get a voltage that I'm expecting between 0 and 5 volts, well, if my analog read is half of the max value, I'm expecting to get half voltage. So not 5 volts, but 2.5. And what do we get? We get 2.5. So that's kind of how that works. There's more information about that in the data sheet, associated with the TMP36. So you might want to read that, and if not, just take it for face value, I guess. The second formula we're going to use is to take that 0 to 5 volt value that we get and turn it into degrees Celsius. So we need to subtract 0.5 volts offset from the voltage. That information, if you're wondering where that comes from, that's associated with the TMP36 sensor, and that information can be found in the data sheet as well. We times that by 100, we get degrees Celsius. So again, we're subtracting that 0.5 voltage from the data sheet, from the calculated voltage, because there is a 0.5 voltage offset, and that's mentioned on page 8 of the data sheet. And then we multiply by 100 to get the temperature in Celsius. Lastly, we take the Celsius temperature and we convert it to Fahrenheit using the tried and true formula that you may remember from grade school, or you may just Google it right now. But essentially, you take your degrees Celsius times it by 9/5 plus 32. And that makes sense because we're timesing it by something that's almost 2. 9/5 is like 4/5, so 1.8, which is almost 2, so we expect a almost double number, and then adding 32 on top of that, so that makes sense. Because anyone who's familiar with a couple key temperatures, their Celsius and their equivalent Fahrenheit, you'll know that 0 degrees Celsius is 32 degrees Fahrenheit, and water boils at 100 degrees Celsius or 212 degrees Fahrenheit. So, this formula just makes sense if you're at all familiar with that. So these three formulas are kind of our algorithm for the program. This page is just basically letting you know that, hey, this temperature sensor does have polarity. So there's a voltage pin and a ground pin. Make sure you hook it up properly. So when you're looking at the sensor, the flat part, the left pin is your voltage, your right pin is the ground, and regardless of what way you're looking at, the middle pin is always the signal. If you hook it in backwards, it'll get really hot. As always, SparkFun provides really good schematics and hookup guides. I'm not going to go over it too much because if you watch my previous video where I go through circuit 4A, I go through the hookup for the LCD in more detail, including why pin 3, which is the contrast pin, is hooked to the wiper of a potentiometer, which, spoiler alert, is basically just to control the contrast of the LCD screen, how well the characters show up. So I won't go over that here, but again, for more information, watch the previous videos. And so what the code is about is really just displaying the temperature readings both in Celsius and Fahrenheit, and if you want to change the temperatures, it says use your finger to press on the sensor, or you can do what I did, use a hair dryer and some sweet and sour sauce. The program overview, again, all you're doing is step 1, you're going to get an analog value from the TMP36 sensor. You're going to convert that into a voltage between 0 and 5 volts. Then in step 2 and 3, you're going to convert that temperature to degrees Celsius and then Fahrenheit. And then you're just going to display that on the LCD. And you wait a second, do another reading. That's all that code does. It's a fairly simple circuit. And a couple of things of note, the code to note, is your voltage conversion algorithms. So many of the sensors you will use with your microcontroller, whether it be Arduino or any other type of microcontroller, work by changing a voltage in some predictable way in response to a property of the world, like temperature, light, or magnetic fields. So then you'll need to build an algorithm that converts these voltages to the desired value in units. And when I say you need to build an algorithm, you need to understand it, but a lot of times the algorithms are almost figured out for you because the calculations are found in the data sheets for the sensor you're using, just like they are in our case. The three equations we're using all came from the data sheet. So again, we're using the equation in order to get the voltage. We're doing our analog read, timesing it by this number, which is obtained by taking 5 volts dividing by 1024. Then we take that voltage, subtract the offset, which again, this information is obtained in the data sheet, times by 100, that gives us degrees Celsius. And finally, we convert our Celsius degrees to Fahrenheit via the standard formula. And now coding challenges. Before I get into the coding challenges, we're just going to look at the actual code associated with Circuit 4A, the code that SparkFun themselves provide. So this is not my coding challenge code, but it's the code by SparkFun. So it's fairly simple. Again, we're just declaring a constant for our temperature sensor pin, A0. We're setting up our LCD stuff, including the liquid crystal library, creating an instance of our liquid crystal class. We've got variables for voltage, degrees Celsius, and Fahrenheit. In setup, we begin serial communication as well as communication with the LCD. This line of code is specific. It basically sets the analog reference to default, which is ensuring that the SparkFun Redboard is using the 5 volt default reference, which if you don't mess with it, that's typically what it is by default, hence the constant that got passed in here. But at one point I changed the analog reference, the AREF associated with the Arduino board, to 3.3 volts and was using 3.3 volts to power the temperature sensor. The reason I was doing that is there's some documentation that says that provides more precise temperature measurements, and so I was just messing with that. And it did seem to work really good, so I'd recommend looking into that yourself. I didn't use it for the video. I went back to 5 volts because, again, I wanted to not overly complicate this. But definitely look into that, and if you have any questions, post them on the forum and I'll respond to them. In the loop, we simply do that calculation where we get the voltage by doing the analog read and timesing it by that number. Might be nice to put this number in some sort of constant, but again, I'm just modifying their code slightly. I also did include, this is code that I included, debug serial print. I created a function down here. That was just so I could see values and follow along what was happening. And then, yeah, I do my 2 other formulas to convert, take the voltage, subtract the offset, and come up with degrees Celsius, and then I turn that degrees Celsius into Fahrenheit, and then I output it on the LCD screen. First row, I am outputting the degrees in Celsius. Second row in Fahrenheit. Technically, I don't need this line per se. Once you clear the LCD screen, the next thing you type will always be at location 00, the upper left-hand corner, by default, but it's nice to be explicit. This line was definitely needed in order to go to the bottom row and the left justified. So that's the code for the original project, so the code provided by SparkFun themselves. And let's just take a look at that. So once that uploads, you'll see a change here, and it'll say degrees C and degrees Fahrenheit. Although that is taking a while to upload, so. Oh, still compiling the sketch. I'm just going to stop that because I think something got hung up there. My computer has been overworked recently, and it is showing by acting up. So I'm not sure why this won't upload, but we're going to kind of force it here by unplugging it. Try again. Okay, so That's the original code. Nothing too exciting. It just shows the degrees, again, in Celsius and Fahrenheit, same as my code. They just included the word degrees first, which I took out so I could know when I was on my code versus their code. And that's pretty much it. So that's their simple code. And now we'll go to my code. Also updating some libraries at the time. I probably shouldn't have done that during the video, but you know, hindsight 2020. So I'm going to get rid of this circuit. I'm going to upload mine. So we'll start by just going through the code. I'll try to be fairly quick because the video is already getting quite long, but I'll start by just letting you know I've done some Doxygen style comments. I'm a really big fan of Doxygen style comments. If you've watched the previous videos, you'll know I like them a lot because of the fact that it doesn't take much to do them. Like if you're doing a multi-line comment anyway, it's a matter of adding an extra asterisk, and suddenly now you have a Doxygen style comment, and then you can add these little @ tags like @file, @brief, @author, @version, @date, you know, in your functions, @param, @return, that sort of thing. And what this allows you to do is take your code and run it through an external program like Doxygen, and it will create very nice professional HTML documentation for you, showing your code. Kind of the same that you would find if you went looking for, you know, if you went to look on CPP reference or any Arduino code references for a particular function or anything, you'd find something that, you know, is really nice and professional, explaining how the function works, the return values, the parameters, and all that. This does that for you automatically by just doing a little extra work when you make your comments. So I really like it. Again, I don't think I fully commented this in Doxygen. I start and then I want to get the videos out and stuff, but definitely something worth looking into. And if you have any questions, feel free to post them and ask away. So basically, what's this function do? Well, according to the @brief, the Arduino program for displaying temperature in various formats using a TMP sensor and RGB LED. Well, excellent. What's that actually mean? Let's see. It means that this program includes a menu system to toggle between different displays. I can display temperature in Kelvin, a bar graph visualization, light sensor, default temperature. You see me do that. It works by using a button for cycling between the different modes and an RGB for color feedback, from totally blue at the coldest to totally red at the hottest. I'm the author. It says version 1.0, but I've changed this stuff a million times, so I haven't really been keeping up with that. But I did make it. I did finalize this code back in early December, so I'm just getting to making the video now. As usual, I include my liquid crystal library so I can use my LCD. I've got a bunch of constants associated with the temperature sensor pin, the light sensor pin, the button. This is the toggle button, the black button, and then my RGB LED pins. So for the red pin, the green pin, and the blue pin, you'll notice they're all on PWM pins because I need to vary the amount of intensity for the red and blue. The green pin I actually don't need at all. I'm not using the green pin. I'm varying from blue, cold, to red, hot, and in between that spectrum. I'm not actually using green. I've got it here included just because I think I originally thought about using the green pin and going through a spectrum of like the rainbow, Roy G. Biv, but I decided against it and just went from blue to red. But it's there anyway in case you want to use it. I've also created some constants representing the minimum and maximum temperatures for the range that I expected. Obviously in real life you'd make these probably some negative temperature and some positive temperature. The range on these sensors is quite large, so you can definitely do that. But considering the room and the temperature in my room is fairly constant, and even to get to these ranges I need to use a hairdryer and sweet and sour sauce. This works out fine for me. These are the constants associated with my LCD pins. So the register select, enable, and the 4 data pins for 4-bit data transfer. I use those constants to create my instance of the liquid crystal library for use as my LCD. The mode variable just determines the menu mode I'm in, i.e. what I'm displaying on the LCD. And then these 3 variables are associated with the button press state and the debounce time and debounce delay. So I'm using this for my debounce. So instead of doing a simple debounce with just a delay, which is blocking code, and it's not really great, even for a delay, which debounce delay, which is really small, usually like 50 or 75 milliseconds. Still, I don't like blocking code, and I don't want to stop my program from working, which is what delay does, even for any amount of time, even a very small amount, especially when I'm doing constant sensor readings. So instead, I like to use time functionality for debounce. I've created a function to convert the voltage that I read in using that formula we've discussed. I read that in, and then I use the second formula, to return a voltage in Celsius. And again, I've used oxygen style comments again here, which are really nice. Let you know the parameter that you take in, the return value, and that can make some really nice documentation. I've also got a function to display the temperature in Kelvin, which just basically again gets the voltage reading by doing the analog read, times it by that number, and then I take that voltage reading, throw it into the convert to Celsius function, as we've seen up here. And that gives me degrees Celsius, and you simply add 273.15 to degrees in Celsius to get it in Kelvin, and then I display it on the LCD screen. Display the bar graph. I do the same two calculations as I did up here, but and get the voltage and then degrees in Celsius, and then I'm mapping that degrees in Celsius. I'm expecting values between the minimum and maximum, and I'm mapping them between 0 and 16. So basically, which is the width of columns in the LCD I'm using. And then I use a for loop to iterate through and basically print a vertical line or a pipe for every, between 0 and 16. So if I had a minimum temperature value at 18, well, I wouldn't print any pipes. If I had maximum temperature value, 30, I'd display 16 pipes, or up to 16. And yeah, so that's pretty much what I do. I don't think I actually, even if I am printing 16, I actually don't display 16, because now that I think about it, I'm printing on the same line 6 digits first. So this is never gonna, this max would be 10, I guess. I might as well update that right now. So, little mistakes like that you notice, and then you fix them. That's what coding is. I have a display photoresistor function. I do an analog read of the light sensor pin, get the light value, and I print it off. Display default, that's where I'm just displaying, I'm doing the same calculation, getting the voltage in degrees Celsius, and then I'm converting that degrees Celsius to Fahrenheit, and then displaying via the LCD. So on the first row, I'm displaying Celsius, and on the second row, Fahrenheit. One thing I've noticed as I've been going through the code, again, it's been a month since I did the code, and I probably meant to fix this and didn't. I do the same calculation where I'm getting the voltage and then the degrees Celsius quite a few times. I do it in display Kelvin, I do it in the display bar graph function, and then I do it again down here in the display default. So in this case, what I probably should have done is taken this voltage reading, put it in my convert to Celsius function, and then simply returned this instead of passing voltage in here. Just return this value and took care of it all in that function, and then just called that function directly, like in all the other functions that are using those same lines of code. Because repeating code like this, it's just not good style. But I'm not going to do that right now. I'm not going to mess with the code at this point. But that's something I would suggest if you're doing your own code and you end up finding that you've repeated the same logic over and over. Definitely put that in a helper function, a utility function, and call that function. That way you can give it a very descriptive name, like get temperature in Celsius, or right. And it's just really descriptive of what's happening, and it's better coding style, I think. Finally, I have this other function, update RGB LED, that takes in a temperature, and I use the constrain function, which basically constrains the difference. I take the difference between the actual temperature that got passed in and the minimum temperature, and I divide that by the range of min to max temperature, what the possible range is. And then I'm mapping that value I'm constraining that value between 0.0 and 1.0. And for more information on the constraint video, feel free to look it up, but I know I'm running long for time, so I'm trying to be a little quicker here. But ultimately, that's going to give me a progress value here, which I'm going to times by 255 to get my red amount. So again, if I end up with a extremely cold temperature, I'm going to end up being mapped really close to 0.0, if not 0.0 at the min. Which means I'm going to have 0 times 255. Well, 0 times anything is 0. I'm going to have 0 red. And I'm then going to have full blue, because the blue, I'm taking 255 minus red. Well, if red is 0, 255 minus 0 is still 255. So I'm going to have 0 red and full blue, which makes sense when it's cold. The other way, if I have, something that maps to almost 1, or 1, I'm going to have 1 times 255. So I'm going to have full red, because 255 times 1 is 255. And I'm going to have 255 minus 255, which is 0. Blue is going to be 0. So that's kind of how the mapping works. And so I analog write to the red pin, whatever value I get, and to the blue pin, whatever value. I always map 0 to green. And I could have called this once in setup instead of calling it every time here. But the overhead on this one statement isn't that much. And I just like it all together. The RGB, it just makes it more explicit that this is a RGB LED, as opposed to if I just had the red and the blue pin. It might just be, people might think it's just a separate LED. So that's why I've kept it back here. But I'm never doing anything with the green LED. Then I have this function for handle the button press. I'm going to try to go a little quicker here. Basically, if the button's pressed and it's an active low button, meaning I'm holding it high via a pull-up resistor. So if you press it, it goes low. If it goes low and the button state has changed, meaning then I'm going to see if enough time has passed. This is my debounce functionality. Basically, I'm going to grab the current time using the millis function minus the last time the debounce happened. And if that duration is greater than the debounce delay, which I think I have set at 50, 50, then I come in and do the function. And what do? Well, first I set button press back to true, so I don't come in here right away again. And I have last debounce set to the current time, so I update that. But the important thing I do is I change the mode. So if you've pressed the button, mode now equals mode plus 1 mod 4. So by incrementing mode and modding by 4, this allows me to toggle from 0 to 4 between the modes, and I never get past 4, because if I'm at mode 3 and there's no mode 4 because I have it set up 0 to 3 for some reason, if I press the button, if I was on mode 3, if mode already equaled 3 and now I come in here with the button change, well, now I'm incrementing mode to 4. Well, mod 4 is 0, so now I go back to mode 0, and then I can increment back up through mode 1, 2, 3, and again, when I'm on 3 again and I come in here, 3 plus 1 is 4, mod 4, I go back to 0. So it allows me to iterate back and forth through all of the things without going past. So that's what's happening there. I probably should have a little more comments in here. I notice I'm a little sparse on the comments. Again, before I put this out to production or anything, I would add a little more comments. Maybe not everything, but definitely things that like this, what this is doing. Like, instead of me explaining it, it'd be really nice to have a comment here explaining that this is allowing me to toggle through the menu options from 0 to 3 and then circle back, wrap around. So we'll just do a quick comment right now, just say wrap around toggle. Not overly descriptive, but something. And then if the button is high, meaning it's not being pressed, I set button press to false. Why? So that I can come in here again. I have a function to display the menu option via the serial monitor, and I have a function to handle serial input. Basically, if there's serial input available, I'm going to use a serial read function, and serial read returns a character, which I put in this variable here, and if that character is between the character 0 and character 3, these are not integers, but if it's between 0 and 3, using this Boolean AND, so if input is greater than or equal to character 0, and input is less than or equal to 3, both these conditions need to be true, then I come in here. Meaning if I have any values, if someone types in anything that's not 0, 1, 2, or 3, the character 0, 1, 2, or 3, then I don't come in here. But if they typed in a correct value, then I come in here and I'm minusing the character 0 from my input. This is to convert a char input to an integer input. So I can go from character 0 to 0 and character 1 to 1. Now this is a little more of a convoluted way to do it. This whole converting, doing a serial read and making that a character and then minusing the character 0 ultimately just to get an integer. There must be an easier way to do that. Well, if you watch my previous video where I go through circuit 4A, you'll see there is an easier way. You can just use serial.parseInt. So instead of this read function, I can use something called serial.parseInt. Correction. And that returns an int directly. But I didn't opt to use that because I like trying different things, and even in my circuit 4A, I use parseInt once and I use the serial.read once, just because, again, the whole point of this course is to learn. And so if I was putting this out to industry, I would make sure everything's consistent, my coding style, whereas when I'm doing it for educational purposes, I like to mix it up. Sometimes I use #define or #define in order to make my constants. Sometimes I use the const keyword in front of my variables. It all depends. But anyway, when that happens, I come in, I select the mode. This mode is now an integer value, and I output that the mode is changed to whoever the mode is. Otherwise, I say invalid input. You'll notice I have all the functions too, because now I'm just getting to set up and loop down here. So I've got all my functions declared above setup and loop, which is typically not what I do. It's not the style I like. I think I did it here just because I was working quick and probably didn't want to make function prototypes, but typically what I would do is I'd put all these functions after setup and loop below the code. That way the first thing I see is setup and then loop, and then I would just have to include function prototypes, meaning take these function headers, the signature, including the return type and the parameters if there is any, and then just end it with a semicolon. I'd have to do that above setup, so before my functions are used, and that's typically what I would do. So I'd use a bunch of function prototypes here. If you're not familiar with function prototypes, please watch my previous video, or feel free to mention it on the forum, and I'll provide you some information. But that's typically what I'd like to do. Just that way I can have setup and loop as the first functions, instead of in this case where we went through all these functions before we even get to setup. But anyway, in setup, I'm setting up my LCD screen using the LCD.begin and then clearing anything that might be on the LCD. I use pin mode to set up all my pins. My button pin is an input pull-up, so I guess I'm using software to use the internal pull-up associated with the Arduino. There's a 20 kilo ohm internal pull-up that you can activate by adding this underscore pull-up to your input. Otherwise, I typically add physical resistors to my buttons and pull them and have them pulled up by having the resistor go to the 5 volts. But either way, use software or physical resistor or both, doesn't really matter. It's up to you. I've set up all my red, green, and blue pins of my RGB as output. Again, I really don't need to set up my green pin because I'm not using it, but I'm just doing it to include everything. I set up my serial monitor, and then I display the menu, and then in the loop I'm handling the button press. I'm checking to see if there's a button press. I'm handling the serial input, continuously checking for serial input. So both the button press and serial input I'm constantly checking for, because that depends what I'm displaying on the LCD. That toggles me between my my different options. Then I have a small delay. That's just to prevent excess CPU usage. I did that because my laptop is old and already sounds like a jet engine. I'm doing this code again that I've called several times. So here I do it one more time, where I read the voltage by doing an analog read on the analog pin. The temperature sensor pin times it by the this number here to get the voltage, and then use that voltage to get degrees in Celsius. So if you remember me saying, I've used this code so many times in various functions, so that I really should have just put this code in the convert Celsius function and called that over and over. So definitely something I'll improve when the video is done. But in either case, I've made the function calls here, and it's got my degrees in Celsius, and then I pass my degrees in Celsius to the function update RGB LED, and that gives me the appropriate color for my RGB LED based on the temperature. And then here's some of the main function of the program. I'm using a switch function to pass in mode, which remember is an int between 0 and 3. Again, it's the current menu display mode. It can be 0, 1, 2, or 3. And so if it's 0, I'm going to display the default, which is just display the temperature in Celsius and Fahrenheit. If it's 1, I'm going to display the temperature in Kelvin. 2, I'm going to display the bar graph. And 3, photoresistor. I'm not doing anything with the temperature, I'm just displaying the photoresistor value. And obviously I have breaks in each case so that I don't just run rampant. I also don't have a default here. You really should always have a default. Obviously I didn't put one, and there's no way for this code really to get into a default mode the way I've got it set up, but it is always good practice. Even if the default doesn't really do anything, I could have simply made the default be the default display mode. That might have been more explicit too, so I had the other modes set up as a thing, and the default would be that mode. So I'll probably update that as well. And then I'm putting a second delay in the code. I'm not sure if I really need that. So let's take it out and see if we need it. Is there anything else? One thing I've noticed too, I might just leave that in for now. Why change it? One thing else I've noticed is that well, I'll just show you. I noticed that I'm showing, I don't know why I did this, but I did, and I'm just looking at now and it's quite funny to me that I've got option 1, option 2, option 3, option 4. I think this was a placeholder menu I put in place because normally I'm more descriptive. I'd be like display temperature in Celsius and Fahrenheit, display Kelvin, display bar graph, display light sensor, and I didn't do that, which makes it funny because then the 0, 1, 2, and 3, 4 would make more sense. In this case it looks funny. Option 1 is 0, option 2 is 1. It's just funny. So there's a couple ways you could fix that. I'm just going to comment on that quickly in case anyone's thinking how weird that is, same as me. A couple ways you could fix that. One, I could change the code right now and change this. Instead of saying option 1, I could just say, you know, display temperature, display temp in, you know, Celsius and Fahrenheit. Jeez, I don't know how to spell Fahrenheit. Fahrenheit, maybe? Okay, you know what? I don't know how to spell Fahrenheit, so I'm going to go with that for now. But I could actually just change the values here. That'd be one option. Or, and I'm not going to do that right now while the video is going, or I could make it so that instead of entering a command between 0 and 3, I could actually just change any values that associate 0 and 3 to 1 to 4. So for example, up here, instead of starting off in mode 0, well, I could start off in mode 1, which could be the new mode 0. Anywhere I'm using the modes 0 through 3, I could just change the code to. So in here, this code actually wouldn't need to change because if I start in mode 1, it's still going to wrap around properly. So I don't think I actually need to change any code there. I might not need to add 1, I guess, but no, even then, I don't think there's any code change needed for here. I would need to change this code. I'd have to put in the character 1 through 4 now. I'd still have to minus 0, so that's all fine. So yeah, I think it's just those two little changes, and obviously change my cases from case 1, 2, 3, and 4 now, as opposed to 0 through 3. I'm not going to do that now, but I was just noticing, and it looked a little silly to me, so I just wanted to comment on it. But it's already done, so now we've went through the code again. I'll do another quick demo, but we've already done it. So really, again, that's the temperature. We can toggle via the menu. So again, I can type in 1 in the serial monitor and toggle to showing the temp in Kelvin. I can type a 2 in the serial monitor, show the bar graph, which again, I'll get more bars if I heat it up. And I can go through option 4 and show the, oh, I typed in something wrong. So typed in option. Oh, I keep typing in option 4. There is no option 4. Yeah, there's only an option 3. So to show my light value, and again, decrease the light. So that's the options. Again, alternatively, I can toggle via the button press. And there's a fairly long press right now that I'm requiring. Not too big of a deal, but after I looked through the code, I realized that long press is due to the fact that I have this 1,000 millisecond delay, so a second delay at the end of my code. And that's why if I press really quick, the button doesn't do anything, because my code is delayed, which is another reason why for button presses or any time I would normally need to use a delay in code, I typically wouldn't use a delay, and instead I would use time functionality like I'm doing here for my button debounce, simply for the fact of, as you can see, delays actually delay code and they stop code from running, so it makes it, in this particular case, I can't click that button really quick, which I can do. If you watch my previous video for Circuit 4A, I had like 4 buttons hooked up and I could press them as quick as I wanted and they worked great. There was no double pressing or anything because I was using time functionality. Whereas here I've got this second delay, so I have to hold down on the button as I press. Not the end of the world. I mean, I know that, but that one I missed, but not holding it down quite enough. Whereas, yeah, if I took that out, either lowered it or just took it out completely, I'm just going to comment it out and see if it makes the difference. So in case you're still watching, we're pretty much done the main code. I'm now showing some changes and showing how we can, as you're noticing errors in a program, or just not necessarily errors, but things aren't functioning quite the way you like them, how you would change that. So there is a little more flickering without the delay. I actually, now that I think about it, that is one good thing that the delay adds. It stops any flickering, especially when, like a temperature value, something that's changing constantly, you get that little flicker. There's other things that we can do with LCD to stop that, but a delay is a very quick way. But now you can see, without the delay, the button response is instant. So again, the delay helps with the flickering, and I guess that's probably why I put it in. It helps with LCD flicker, but it makes it so that I can't do this with the button press. So, there's different options you could do. There's different ways that you could avoid the flicker that's happening with that with the screen, especially with values that change all the time. Maybe a good compromise is have a smaller delay. Maybe 200 milliseconds would be enough to help ease some of that flicker, that LCD flicker, but still allow the button to be fairly responsive. So let's just take a look at that and see if that makes any difference. So here the flickering doesn't look bad to me. I mean, there is a little flicker, but nothing major. And the button is still very responsive. So maybe that's the compromise that we need. Anyway, I'm going to go over a couple other things. Just wanted to show you guys the... so again, firstly, this is the coding challenges that we did over. We displayed the temperature in degrees Kelvin by adding 273.15 to the Celsius temperature. I displayed the temperature as a bar graph. I swapped out the TMP36 sensor for another sensor, in this case a photoresistor. I didn't really swap it out, I just added a photoresistor capability, and I added an RGB LED that changed color based on the temperature. A couple things I just want to point out too. If you do end up going looking up the TMP36 datasheet, you'll end up seeing there's lots of stuff to read in here. You'll find lots of good information about the sensor. In particular, the TMP36 is specified from -40 degrees Celsius, which is -4 degrees Fahrenheit actually as well, to 125 degrees Celsius, which is 200 and some Fahrenheit, I guess. And it provides a 750 millivolt output at 25 degrees Celsius and operates to 125 degrees Celsius from a single 2.7 volt supply. The TMP36 is functionally compatible with the LM50. And here's the scale. The TMP36 has an output scale factor of 10 millivolts per degrees. So the calculations we did ultimately result in giving us 10 millivolts per degree. So every 10 millivolts that is output via the sensor relates to 1 degree Celsius. It's a 3-lead pin. It's in a TO92 package. It comes in other packages as well, but the one we're using is this. This is the pinout you see from the bottom. Again, the left pin, when you're looking at the flat side, is your voltage source. The middle pin is your V out or your signal, and the right pin is your ground. Again, you could go through this at your leisure. If you're ever really bored and just hate life, feel free to read through this data sheet completely. Otherwise, most of the information that you need just to get up and using it is in the SparkFun Inventor's Kit Guide, or there's a little more information on the actual website. But this just kind of shows you to how the temperature sensor is linear. So where's the voltage current one? This is the output voltage to the temperature. So B corresponds, this B line corresponds with the TMP36 sensor, and then there's also 35 and 37, but this is R1, and you can see that it's linear. As the voltage output increases, the temperature increases, so it's, has a linear relationship there. What else do I want to show you on this? This is the offset. Again, that's where we got that 0.5 offset that we were subtracting. As you can see, it's only associated with the TMP36. If we were using the 3537, we wouldn't have an offset. We'd have a different calculation, but we wouldn't have an offset. And yeah, I think that's pretty much all the information on the data sheet that I highlighted. I mean, there's a lot more information here than you need just to get using it. That's the thing, these sensors are so simple to hook up and use. You don't need all that detail, but it is nice to read and kind of figure out what's going on. There's also this other guide. This is from Adafruit, and this just has some information too I thought was pretty good. And it's definitely more digestible than a data sheet. Basically, again, it just talks that this is an analog temperature sensor for reading ambient temperature. This sensor in particular uses solid state technology to determine temperature, which is different than some other temperature sensors in the past. Like mercury is used in old thermometers. Some home thermometers or stoves use biometric strips. Thermistors are used in temperature sensitive, which are thermistors or temperature sensitive resistors. All these other type of technologies can be used for temperature sensors, but this particular temperature sensor uses solid state technology, which the fact that it does this, it uses the fact that temperature increases when the voltage across a diode increases at a known rate. And the good thing about this technology, using this technique where we know the temperature increases as the voltage across the diode increases at this known rate, this allows for more precision. So by precisely amplifying the voltage change, it's easy to generate an analog signal that is directly proportional to temperature. So essentially that is how the temperature is measured. We're amplifying the voltage change and generating an analog signal that is directly proportional to temperature. And that might sound complex, but it doesn't matter. It's all done for you inside the chip. Just know that it's a fairly accurate chip. And again, the right pin here, or the left pin, correction, when you're looking at the flat edge, you can get anywhere from 2.7 to 5.5 volts. The analog out signal is in the middle and ground on the other end. So again, the great part about this sensor, no moving parts. It's precise, never wears out. You don't need to calibrate it. Again, no moving parts. And it can work under many environmental conditions. And it's constant between the sensors and readings. So yeah, and very inexpensive, easy to use. So that's, its claim to fame right there. A couple other details about it. Again, temperature range, negative 40 degrees Celsius to 150 degrees Celsius. And negative 40 Fahrenheit, because that's where Celsius and Fahrenheit meet, up to 302 degrees Fahrenheit. The output range, again, 0.1 volt is what this sensor is going to output at negative 40, and it's going to output 2 volts at 150. So you see, it's not actually outputting like 0 to 5. It's outputting a small range. And it has a power supply from 2.7 to 5.5, small current draw. How the temperature is measured. So again, the left pin is you hook to power, the right pin is to ground, and the middle pin will have an analog voltage that is directly proportional, i.e. linear, to the temperature. And that was I showed you that in the data sheet as well. This is here as well. So again, the analog output voltage is directly proportional to the temperature. So directly proportional, has a linear relationship. So to convert the voltage to temperature, we have this basic formula. It's the same one we used before. The output voltage minus that offset, 500. It's 500 instead of 0.5 because in this case this calculation is showing the V out in millivolts. So 0.5 volts is 500 millivolts. Divide by 10. Again, normally it would be times by 100, but again, the divide by 10 thing is happening because this calculation is showing it in millivolts as opposed to volts. But either way, doing this will still get us our temperature in Celsius. And my apologies. And then testing temperature sensor. This is something I did want to go over. I do this in a separate video, I believe. When I first was fiddling with this back in early December, I wasn't sure if the sensor was working. It ended up being something else, some of my troubleshooting issues. But needless to say, I thought there was something wrong, so I went and learned how to test it. So basically, the way to test the sensor to see if the sensor is actually working and it's not screwed up, because again, these sensors are very susceptible to static electricity and all that sort of thing, which is why it's always good practice to wear an ESD, an electrostatic discharge strap, when you're dealing with circuits. But because of that, I wanted to verify if it was working, so I did this little test. Basically, you use an external power supply source, whether it's a pack of batteries or I actually have an external power supply hooked up here on the bench, and you give it between 2.7 to 5.5 volts, and then you use a digital multimeter to read the pins basically, and at room temperature about 25 degrees Celsius you should be outputting about 0.75 volts. And so if that happens, then you know your thing is working, your sensor is working. So I'm going to show you how I did that. So again, I've got a digital multimeter right here. I'm going to set it on voltage reading. Hoping that shows up for you guys. So that's on voltage reading. I've got an external power supply that I'm going to hook up. So first I'm going to unhook the sensor. We know it's working, and it's about 25 degrees in here, so we should expect to get a voltage of 0.75. I know it's working, but I'm going to pull out the circuit. I've got my ESD strap on, as you should. I'm going to hook up the power supply to the circuit. Remember, the left pin is the voltage pin. The right pin is the ground. So that's hooked up there. I'm going to put voltage through that in a minute. Right now I've got nothing on it, but I've got my multimeter hooked up to here, and I'm going to read. It's going to be hard to do. I'm going to read off the middle pin. It's really hard to just get off that, but I'm going to do that. So I think I'm just touching the middle pin and hopefully not grabbing any of the other. Hook this up to ground. So this is a lot of, it's a very small sensor. Kind of hard to do this. If you had two people, you might not need to use these alligator clips, but I do for this purpose. So again, what I've got connected here, it's a little hard to see, but on the left pin, I've got my power supply hooked up from my external power supply, and then also on the right pin hooked to ground, the external power supply. And then the digital multimeter leads, the negative is hooked up to the ground, and the positive is hooked up to the middle pin. I'm going to turn my power supply on. And it is on. .5 volts. So it's on 4.5 volts, and so I should be reading around 0.75 volts maybe. And you can see there that, keep the wires separated, I'm at 4.5 volts, and I'll up that to 4.25. Okay, so I'm at 5 volts right now, and you can see I'm reading 0.72 volts, which means that the sensor is working. Because again, at 0.75 volts is kind of what I should be reading at 25 degrees. And, it's probably a little less than 25 in here. I've shown 25 a minute ago. But, again, that could be the wires, again, fiddling with the wires. So this is showing the sensor that's accurate. So it works good. I'm going to shut that down. So again, do that if you have a sensor that you feel may not be working properly. Obviously, if you have more than one of these sensors, the easiest quick fix is just to replace it with another one and see if your circuit suddenly works, and in which case it probably is bad, or at least needs some investigating. But otherwise, you can do that little test on it. And let me just put this back. Okay, so yeah, I just wanted to show that little test. If you ran into any issues, it's a nice little troubleshooting test you can do. Again, when you had it hooked up, you can touch it with ice, you can touch it with your fingers, get it hot and see the temperature change. I did that the first time, but it's hard to do it with a video. This is also, again, this guide from Adafruit just has a lot of good information. It basically shows you the TMP36 doesn't act like a resistor, so it works a little different than your photocells and other things. And there's really only one way to read the temperature value from the sensor, and that's by plugging the output pin directly into your analog pin, so your ADC converter, analog digital converter input. That's pretty much that. Again, they show you this sketch. They give you a couple sample sketches showing, taking off the 0.5 offset, 10 millivolt per degree Celsius. Lots of information there. This is what I was talking about earlier, that I had practiced with this before back in early December. You can get better precision by using a 3.3 volt reference voltage as your AREF, and your AREF is right here, instead of the 5 volts. And it'll be more precise and less noisy. So you probably noticed there was a lot of noise if I wiggled the wire in this circuit, especially when I was using the sweet and sour sauce to cool down the circuit. That is just a big package, and it was pushing wires every which way, and it caused a lot of jumping in temperature. I had less of that when I used the 3.3 volt. So if you guys are interested in trying that on your own, definitely I would hook it up like this. Again, instead of going to the 5 volt, go into 3.3 volt and hook the 3.3 volt up to your AREF, so that's your reference. As opposed to 5 volts, which it is by default, which is why I had that line of code, because I had previously messed with it. But it will give you a lot better precision. And this, you don't need this. This is just kind of extra stuff, photo sensor thing. Just hook up to ground and volts. So the code will look like this. You do something like this. You define AREF voltage as 3.3, and then you would just when you're doing your temperature reading, you would do times it by AREF instead, and just a couple little different calculations. But I'll let you guys look that up. I'll include the links for this document as well as the data sheet, which I think is already included in the SparkFun guide, but that's pretty much it. So I know it's been a long video, over an hour, but I appreciate you guys watching. If you have any questions, again, feel free to post them to the forum, and I'd be happy to answer anything. But again, like I said, have fun. There's a lot more happening on this circuit right now than a lot more. See, again, me just fiddling with the wires got back down to normal temperature than when it was like 37. So again, that is less of a thing when you use the 3.3 volts, more precise. However, the wires fiddling would still probably cause a little bit of reaction. But yeah, if you have any questions, let me know. Post them on the forum. Go have fun. Work with circuits. It's a lot of fun. I'm going to make this video a little longer, but feel free to leave at this point if you want to just figure out your own troubleshooting. I will just talk briefly about some of the troubleshooting I ran into. I encountered several issues with this project and the code. Though I initially had it working fine, the only problem that
The temperature readings on the LCD were widely inaccurate. Again, around they were like 400 degrees Celsius and 700, and 70 degrees Fahrenheit, that sort of thing, which clearly wasn't right for the room. Again, I have a hot room down here, but it's definitely not that hot. One of the issues was the wires connecting the breadboard to the 5 volts and ground were a bit tight, and so they basically kept coming out. That caused some interference. The TEM36 sensor is highly sensitive to noise, so that's why I've kind of kept reiterating that, because that was a major issue. I mean, even during today's demo, we can see it's working now, but if anything becomes loose at all, again, if the power wires become loose a little bit, see how this, I'm just messing with the power wire from the Arduino there to the breadboard. You can see how the sensor's jumping all over the place. So very sensitive to the wires moving around. So just keep that in mind. If you're doing this project yourself, really make sure your circuit, the wires aren't too tight pulling like they kind of are in mine a little bit, and that you're using good wires. I recommend going on Amazon and buying some DuPont cables. They're just nicer wires than the ones that come in the kit, but teach their own. Another issue I had, one of the biggest issues actually, was I was using analog pin A5 at first. The reason I was using it is because I've got multiple circuits hooked up at once sometimes, as you can probably see here. I've got like a motor circuit hooked up for Project 5. So because I've always got various circuits in production, I wanted to use A5 originally, and I just wasn't getting any readings. That's when I started looking into the temp sensor a little more. I did the test on the temp sensor with the volt with the digital multimeter, and it all worked and said the sensor was great. And it turns out that it just was the pin that didn't work at all. So my A5 pin just doesn't work, which is funny because it was the first time I used the A5 pin, and it just doesn't work. I tried it on other pins. All the other pins work. I tried the A5 pin with just another simple code, one of the example codes from the Arduino IDE on the A5 pin, and the pin is it's a bad pin, I guess. And it's unfortunate because obviously I'm losing one of the pins, but what was more unfortunate was I wasted so much time not thinking it was the pin. So if you get into an issue and you've tried a lot of different things and you just don't know what's happening, check if the pin's not working. I mean, it's possible. These are electronics. Not everything's perfect, right? So finally, I think in addition to troubleshooting the pin, I did some research on the TEM36 sensor, and I learned that you can use an external power source, an analog voltmeter, or digital multimeter to test the sensor's functionality, which I did, and ruled out the hardware. So that's what I just showed you guys with the bench power supply and the digital multimeter. But anyway, so that's it. This has been an extremely long video. If you followed it, thanks a lot. Hopefully you learned something both about the temp sensor, the LCD, and you learned something from my coding challenge. If you have any questions, post them on the forum and I'll be happy to answer them. Thanks for watching.